Greetings to dear students. In this video, we are going to see about how to find the value of a definite integrals using Cauchy's residue theorem. Okay. So, yeah. So I hope the screen is visible to everyone. The calculus of residues theorem provides a very efficient tool for the evaluation of definite integrals. Okay, so here we have 6 types of integrals. For these types of integrals, by how we are going to apply the Cauchy's residue theorem to find or evaluate the value of different integrals. So let us see one by one. So the type 1 is the integrals of the form integral 0 to 2 pi r of cos theta comma sin theta d theta, where the integrand is a rational function of cos theta and sin theta. So what are the requirements we have here? The integrals, the upper limit and lower limit is 0 to 2 pi, and the integrand is a rational function. It's a combination of cos theta and sin theta. Okay, so these are the two requirements. So there are 3 steps to find the value of the particular integral. So step 1 is, so first note that the given integral is in the polar coordinates, okay, is in the polar coordinates. So first we are changing the terms into the Cartesian coordinates, okay. So so step 1 is convert the given function r of cos theta comma sin theta in terms of z by substitute z equal to e power I theta. Okay, so let us take z equal to e power I theta. So now what are the values we need? The value of cos theta, sin theta and d theta. Okay, so we have z equal to e power I theta. By differentiating both sides we get dz is equal to I into e power I theta d theta. By simplifying we get d theta is equal to minus I dz by e power I theta. Okay, so d theta is equal to minus I into dz by e power I theta. So already we took e power I theta as z, so therefore we get d theta is equal to minus I dz by z. So therefore the value of d theta in terms of z is dz is minus I by z into dz. Okay, so now so far now we have found the value of d theta. Now it's time to find the value of cos theta and sin theta in terms of z. Okay, so already we know that z equal to e power I theta, and e power I theta is nothing but cos theta plus I sin theta. This is Euler formula, cos theta plus I sin theta. Also we have 1 by z is equal to 1 by e power I theta is equal to e power minus I theta, which is nothing but cos theta minus I sin theta. By summing, we get the value of cos theta in terms of z. By subtracting, we get the value of sin theta in terms of z. So what is the value of cos theta? Cos theta is equal to 1 by 2 times z plus 1 by z, and sin theta is equal to 1 by 2 I z minus 1 by z. So we have found all the required values, okay? Cos theta, sin theta and d theta. So next step 2 is what? Step 2 is we are going to substitute the value of cos theta, sin theta and d theta in the given integral. Okay. So by substituting the value of cos theta, sin theta, d theta, we get integral over 0 to 2 pi r of cos theta sin theta d theta is equal to this term. Here we know that we are changing the terms in polar coordinates into Cartesian coordinates, isn't it? So in polar coordinates, 0 to 2 pi is what? Is a circle. It's a circle, isn't it? So in in Cartesian coordinates 0 and radius 1. So 0 to 2 pi in changing as mod z equal to 1. Mod z equal to 1 means is a circle with the center 0 and radius 1. That is mod z minus 0 equal to 1. Okay. So step 2 is nothing but we are substituting the value of cos theta, sin theta, d theta in the given integral. Okay. Step 3 is by using Cauchy's residue theorem, we are going to evaluate this integral. Okay. So if you see an example, you will get idea about how we have to find or we need to find the value of the integral of the form type 1. Okay. So evaluate integral 0 to pi 1 by a plus cos theta d theta where the value of a is greater than 1. Okay. So the given integral is integral 0 to pi 1 by a plus cos theta d theta. So the integrand is a rational function, which is a combination of cos theta. Okay. So it is clearly of type 1. But note that the integral is not 0 to 2 pi. It's only up to 0 to pi. But we know that cos theta takes the same values in the intervals 0 to pi and pi to 2 pi. So it is clear that the integral 0 to pi is 1/2 of the integral from 0 to 2 pi. So therefore, integral 0 to pi 1 by a plus cos theta d theta can be written as 1 by 2 times integral 0 to 2 pi 1 by a plus cos theta d theta. Okay. So now it is clearly in the form of type 1. Okay. So what is the step 1? We have to substitute the value of cos theta. Sorry, we have to find the value of cos theta and d theta. So already in the process of the steps in the procedure, we have already found the value of cos theta and d theta. So here we are going to substitute that value in the given integrals. So integral 0 to 2 pi 1 by a plus cos theta d theta is equal to, it's changed into integral when we are changing into Cartesian coordinates. So therefore, which is equal to integral mod z equal to 1 by a plus the value of cos theta is 1 by 2 z plus 1 by z. The value of d theta is minus I by z dz. So after simplifying this, we get, okay. So after simplifying this, we get minus 2i integral mod z equal to 1 by z square plus 2a z plus 1 into dz. So therefore, the given integral 0 to 2 pi 1 by a plus cos theta d theta, which is equal to minus 2i integral over mod z equal to 1 f of z dz, where f of z is nothing but 1 by z square plus 2a z plus 1. So what is the next step? We have to use the Cauchy's residue theorem to evaluate these integrals. To apply Cauchy's residue theorem, what are the things we need to know? What are the poles of the given function, isn't it? So first we find the poles of the given function. Okay. So for that, we are going to factorize the given equation into, so we are going to factorize the given equation. Okay, so the given equation is a what is it? It's a quadratic equation. So we are going to factorize the equation into linear. Okay, so first we find the roots of the given equation. Z square plus 2a z plus 1. It's this regular one. By using the formula, we are find the roots of the given equation. So the roots are minus a plus square root of a square minus 1, which is denoted as alpha, and the another root is minus a minus square root of a square minus 1, which is denoted by beta. Okay, but we have f of z as 1 by z square plus 2a z plus 1. So therefore f of z is equal to 1 by z minus alpha into z minus beta, where alpha and beta are roots of f of z. Okay, not f of z, roots, sorry, alpha and beta are roots of the quadratic equation z square plus 2a z plus 1, and alpha and beta are poles of f of z. Okay, alpha and beta are roots of, for which quadratic equation, z square plus 2a z plus 1. Okay, z square z square plus 2a z plus 1, but alpha and beta are poles of f of z. Okay. Okay. So now we have the region is mod z equal to 1. Next, what we are going to do is we are going to find whether these two roots, these two poles are lies inside the region or outside the region. Okay. So for that, take modulus of b. What is modulus of b? It is equal to minus a minus square root of a square minus 1, which is equal to a plus square root of a square minus 1. But given that the value of a is greater than 1, so therefore modulus of b, the value of modulus of b is obviously greater than 1. So which means the pole beta lies outside the region. Okay. So next we check the pole alpha. We know that product of the root is 1. Okay, how? Since the quadratic equation is z square plus 2a z plus 1 and alpha and beta are roots of the equation, we have the product of root is the last one, that is the, this one, the constant term. The constant term is 1. So the product of the root alpha beta is equal to 1. So modulus of alpha beta is obviously 1. So from this we get modulus of alpha is equal to 1 by modulus of beta. As modulus of beta greater than 1 by modulus of beta is less than 1. It shows that the pole alpha lies inside the circle. Okay. So now we are ready to apply the Cauchy's residue formula for the poles. Since the pole alpha only lies inside the region, it is enough to find the residue at the pole alpha alone. Okay. So since alpha is a single pole, residue of alpha, residue of f of z at the pole alpha is equal to, by definition, limit z tends to alpha, z minus alpha into 1 by z minus alpha into z minus beta, z minus alpha is alpha will get cancelled. So we get limit z tends to alpha 1 by z minus beta. When z tends to alpha, this becomes 1 by alpha minus beta. We know the value of alpha and beta. By subtracting, we get 1 by 2 times square root of a square minus 1. Okay. So the residue of f of z at the pole alpha is 1 by 2 into square root of a square minus 1. So now we are going to apply Cauchy's residue theorem. What is Cauchy's residue theorem? 1 by 2 pi I integral over mod z equal to 1 f of z. And here we have the region as mod z equal to 1. In general, the region C. F of z dz is equal to sum of the residues. Here we have only one pole alpha. So therefore the residue of alpha is 1 by 2 into square root of a square minus 1. So from this we need only the value of integral over mod z equal to 1 f of z dz. So 1 by 2 pi I goes the right hand side. It is equal to 2 pi I into 1 by 2 into square root of a square minus 1. By simplifying we get pi I into pi I divided by square root of a square minus 1. So from equation 2, this integral over mod z equal to 1 f of z dz is equal to integral over 0 to 2 pi 1 by a plus cos theta d theta. Sorry, what is in the equation 2? Equation 2 is 1 integral 0 to 2 pi 1 by a plus cos theta d theta is equal to minus 2 I times this one. Okay. So we have found the value of integral over mod z equal to 1 f of z dz. So we are substituting the value of integral over mod z equal to 1 f of z dz in this place. Okay. So we get, yeah, we get integral over 0 to 2 pi 1 by a plus cos theta d theta is equal to minus 2 I into the value of integral over mod z equal to 1, sorry, integral over mod z equal to 1 f of z dz, which is nothing but pi I by square root of a square minus 1. By simplifying, we get 2 pi by square root of a square minus 1. But the actual integral is integral 0 to pi, isn't it? So integral 0 to pi 1 by a plus cos theta d theta is equal to 1 by 2 times integral 0 to 2 pi. So what is the value of integral 0 to 2 pi? It is nothing but 2 pi by square root of a square minus 1. So by simplifying, we get integral over 0 to pi 1 by a plus cos theta d theta is equal to pi by square root of a square minus 1. Okay, so simple one. If the integral is of the form cos theta sin theta, then you have to replace or you have to change the values in terms of z. So for cos theta, we have the value as 1 by 2 into z plus 1 by z. For sin theta, 1 by 2 I into z minus 1 by z, and d theta is equal to minus I by z dz. Okay, by substituting the value of cos theta sin theta d theta, the given integral is changing into Cartesian coordinates. And again, after changing into Cartesian coordinates, we have to find the roots and sorry, we have to find the poles of the given function. After finding the poles, we have to the next thing is to check whether the poles lies inside the region or outside the region. After finding that, we are going to we need to apply the Cauchy's residue formula. Okay, so I hope this problem is clear to everyone. So in next video, we will see the another types of integrals. Okay, so here totally we have 6 types. So already in this video we have seen the first type. In the upcoming videos we will see the next types. Okay, so thank you, dear students. We will meet on the next video. Thank you.